Hello students, welcome back to today's class. We are still investigating the pressure volume diagram. So in the pressure volume diagram, for each constant pressure there is a constant point of definite specific volume at which vaporization is complete. For pressure PP, PQ and PR, these points are P prime, Q prime and R prime, and may be joined to form a line as seen in figure 2.2 called the vapor line, which relates the pressure and the volume. You can see it's a curve drawn, and this curve, when we now combine the figure 2.1 we discussed in our previous video, the figure 2.1, this one here and this figure 2.2 are combined and extended to a higher pressure, they form a continuous curve or loop with a turning point called the critical point. So point C, which is the critical point as indicated in the figure 2.3. So this is the figure 2.3. the first curve is that of the pressure of figure 2.1. we had P, Q and R, and the pressure volume diagram of figure 2.2 as we have R prime, Q prime, P prime. When we combine these two graphs we get the critical point, and that is called the critical pressure. So then the pressure at that point is called critical pressure. Saturation state. The saturation state is a state at which a change of phase may occur without change of pressure or temperature. For instance, you have P, Q, R, P prime, Q prime and R prime. The substances existing within the loop, e.g. at point S in the figure 2.3, point S in the figure 2.3, whatever is within the loop, you can see where S is, it is sandwiched in between these two curves. So that point S is referred to as the wet vapor, while the vapor along the saturated vapor line is called the dry saturated, and no liquid is present in the vapor in this state, i.e. along the vapor line R prime, Q prime, P prime. The lines of constant temperature are called isotherms, and this can be plotted on a pressure volume diagram as shown in figure 2.4. So this is the figure 2.4 where we have lines of constant temperatures, and we refer to those lines as isotherms. So you can see how T1, T2, T3 they change, they are constant, they are constantly drawn. So we have isotherms. So these lines are horizontal in the wet vapor regions. The isotherm lines, they are horizontal in the wet vapor region. For each pressure there is a corresponding saturation temperature, e.g. for pressure PQ the saturation temperature is T2. When a dry saturated vapor is heated at constant pressure, its temperature rises and its vapor becomes superheated. The difference between the actual superheated temperature and the saturation temperature at the pressure of the vapor is called the degree of superheat. So in figure 2.4 we have the degree of superheat, and you can see the isotherm, whatever is within the wet vapor region, the T's, and the ones along the curve is called the dry vapor. So the degree of the superheat is shown in this figure. The vapor at point S is superheated at pressure PQ, and the temperature T3, and the degree of superheat is T3 minus T2, i.e. Ts minus Tq prime. And for a wet vapor, the temperature and pressure are not independent, since they remain constant for a range of values of the specific volume. The condition or quality of a wet vapor is frequently defined by its dryness fraction. When the dryness fraction and the pressure or temperature are known, then the state of the wet vapor is fully defined. So dryness fraction X is equal to mass of the dry vapor in 1 kg of the mixture. So let's discuss about perfect gas. At a very high degree of superheat, an isotherm on the pressure volume diagram tends to become a hyperbola, obeying the law of the pressure volume being constant. So the isotherm, for instance, if we pick the isotherm T6 in this figure, you can see it curves it curves perfectly like a hyperbola, So when an isotherm follows a hyperbola law, the equation of state is pressure times volume divided by temperature, which is constant, is satisfied. This is the equation of an idealized substance called a perfect gas. So the working fluid in practical engineering problems is either a substance approximating to a perfect gas, e.g. air, or a substance that exists mainly as liquid and vapor, e.g. steam and refrigerant vapors such as ammonia and freon. For those substances approximating to perfect gas, certain laws relating the properties can be assumed. For the substances in the liquid and vapor phase, the properties are not related by definite laws, and values of the properties are determined empirically and tabulated in a convenient form. So students, this we will reinforce with interpretation of given questions that we will look in a physical class as we interpret the steam tables and the molar charts. So this marks the end of our today's meeting. Let's again meet in the next class.